Greetings, physics enthusiasts. Welcome to AP Physics 1, Unit 2, Lesson 1. So we are finally in Unit 2. Very exciting. As we enter Unit 2, we start to look at what I call the antecedent of motion. So what do I mean when I say the antecedent? I kind of mean the cause of the motion. So prior to this video, in Unit 1, we described motion. We talked about whether something was moving to the right or to the left. We talked about if its velocity was constant or if its velocity was changing. And we quantified that change in velocity and called it acceleration. So to speed up or to slow down is to accelerate. And the rate at which the velocity changes is acceleration. So you remember that, right? Acceleration is the rate of change of velocity. 5-word definition of acceleration: rate of change of velocity. Or as an equation, acceleration is delta V over t. So we described that and we said things were accelerating, but we didn't say why they were accelerating. We didn't say what the antecedent of that acceleration was. So that is what we are going to start studying now. Now, this new topic is called dynamics. Something that is dynamic is something that changes. And so the velocity might be changing. And so when we look at why that velocity might be changing, what the cause of that acceleration is, we call that study dynamics. So previously, again, we said acceleration is delta V over t. That's the definition of acceleration. But now I want to say acceleration equals, and I'm going to look for the cause of the acceleration. So what I'm going to do is I'm going to write a fraction bar here. I am going to say acceleration is some quantity over some other quantity. And I want you to think for a few moments about what you think goes in the numerator and what you think goes in the denominator. What things, if they are bigger, make the acceleration bigger? Well, they would go in the numerator. What things, if they are bigger, would make the acceleration smaller? Those things go in the denominator. So these things in the numerator, and actually there's just one, would be in direct proportion with acceleration. What goes in the denominator would be in inverse proportion with acceleration. In other words, if this, I could draw an up arrow. If this increases, acceleration increases. But if this increases, acceleration decreases. All right, you should probably pause the video for 30 seconds right now and just think, what would I write here in the numerator that's in direct proportion with acceleration? And what would I write in the denominator that's in inverse proportion with acceleration? So think about that for a moment. All right, and now that you're done thinking about that, I'm going to tell you that what goes in the denominator, just because my pen went here first, is mass. The mass of an object is inversely proportional to acceleration. So think about, well, I'm going to tell you that, and then I'm actually going to talk about it in a second. So let's talk about the numerator first. Force. What is a force? Force, I just mean a push or a pull. And if I push something harder, bigger force, it's going to have a greater acceleration. And if I push something less hard, it's going to have less acceleration. And if nobody pushes it, F is 0, then there's not going to be acceleration. So what we say here, force causes acceleration. Very important sentence. Force causes acceleration. A lot of people incorrectly think that forces cause motion. No. Forces cause acceleration. Now, what about m, mass, being here in the denominator? Well, imagine if I'm pushing two different things. Let's say I'm pushing a little toy car, and then I'm pushing a big real truck. If I push them both with the same amount of force, we'll talk about what that unit is later, but the same hardness. If I push a little toy truck and I push a big truck, you know that the little toy car is going to have a much larger acceleration. And the reason is the toy truck has less mass, and therefore with the same force exerted on it, it would have a greater acceleration. And a big truck, if there's a semi truck sitting out there in the parking lot, I might push it really, really hard. But it's got such a large mass that it's going to have a very small acceleration. So this equation, A equals F over m, is one of the fundamental, basic, most important equations in physics, A equals F over m. And what it says is that acceleration is directly proportional to how hard the object gets pushed, and acceleration is inversely proportional to the mass of the object. This is called Newton's law, because Sir Isaac Newton did a lot of work with forces. Were it me, I would call this just Newton's law. Turns out that Newton has multiple laws, and they call this his second law. Let's not worry about Newton's first law, because this is the one that really matters. So it's called Newton's second law. The other thing that's a little weird about this is, we've got a fraction and some people are uncomfortable with fractions. So could I rearrange this? Could I write m equals F over A? Same thing. Could I write F equals MA? All of these are the same thing. This one has A by itself. This one has M by itself. This one has F by itself. If you were to walk around JPL and ask 100 people, hey, what's Newton's second law? My bet is that all of them would know what Newton's second law is. And my bet is that almost all of them would say this answer and not these two. And I understand why people go for that. F equals ma, it's more commonly said, you don't have to worry about the fraction. But for us, we're going to say A equals F over m, because it talks about acceleration being the result of force and mass. See, if I write F equals ma, it almost seems like A or m are causing the force. And that's not what I want to say. I want to say that the force causes acceleration and mass works against or hinders or resists acceleration. I like the word resists because you learned probably in junior high that inertia is resistance to change, and mass is another word for inertia. All right, so there's a very, very important equation. Now, another thing I want to say is that this F, what if there's a couple different forces acting on an object? What if I talk about my calculator here and somebody pushes it to the right and somebody else pushes it to the left? Ooh, well, is it this force that's causing the acceleration, or is it this force that's causing the acceleration? Well, it turns out that F means net force. Net, the overall sum. So it's the sum, that's the Greek letter sigma, that means the sum, add them all up, the sum of all the forces. Or we could write F net. All of those mean the same thing. So even though this just says F, it really means the net force. So if someone's pushing my head with a 10 Newton force to the right and someone else is pushing with a 2 Newton force to the left, 10 plus 2 adds up to 8. So F would be 8. So it's the net force. And so one way that we usually organize that is we draw what's called a free body diagram. So the body is free. There's a thing that's not nailed to the table. If it's nailed to the table, it's not going to accelerate. But if it's free to accelerate, then we can have a free body diagram. And all that is a little box that represents the object. So if I'm talking about everybody pushing the piano, we don't have to draw a three-dimensional piano. We don't have to make sure there's 88 keys, and we don't have to decide whether or not there's going to be a middle pedal. It doesn't matter. Just draw a box. And then we draw arrows on the box. I noticed recently when I was looking at student work that a lot of times people were drawing segments to represent velocities. Remember, you have to have an arrow on one of those sides to represent a velocity because velocity has a direction. So be careful when you're talking about a vector quantity that you draw an arrow. So we should draw arrows on here to represent forces. So if somebody pushes this object to the right, and somebody else pushes the object to the right, and then somebody else pushes the object to the left, each of these arrows would represent a force. And we could keep track of it that way. And doesn't matter where I place the arrow, what matters is that the arrow points to the right. So these two arrows would both be positive, and then this arrow would be a negative force. So it's not where the arrow is placed, it's what direction the arrow points. All right, and so those arrows are there. Let's talk about the unit for force. So I want to label these, but I realized, if I want to label this one 10 and this one 6 and this one 5, those 10 what? 10 force units, 6 force units, 5 force units. So let's talk about the unit for force. F equals ma. So that's one of the ways we can write Newton's second law. What is the unit for mass? The unit for mass is the kilogram. You knew that. What is the unit for acceleration? It's meters over seconds squared. You knew that. We talked about that in previous videos when we defined acceleration. So what's the unit for force? Well, the unit for force is kilograms times meters per second squared. So right there, the unit for force. So, the unit for distance is meters. The unit for time is seconds. The unit for acceleration is meters per second squared. The unit for velocity is meters per second. And now we know the unit for force. You should put this in your table where you've got all the units listed on the left and the quantities listed on the left and the units listed on the right. The unit for force is kilograms times meters per second squared. There you go. Now, that takes 10 syllables to say kilograms times meters per second squared. So sometimes we have an abbreviation for units. I don't think that's a good idea, but they are out there. So what we tend to do is we tend to take scientists, who have made a positive contribution to science, and we say, ooh, let's name them. Let's name this after that scientist. So maybe we should call this the David, because I've made so many. No, we're not going to name it after me. No. So Sir Isaac Newton made a lot of contributions. And so we are going to call this the Newton. So the unit for force is really kilograms times meters per second squared, or we can say the Newton, abbreviated capital N. So this is 5 newtons, 6 newtons, 10 newtons. The total force is 15 to the right, 6 to the left. So the total net force is 9 newtons to the right. So the Newton is another way of saying kilograms times meters per second squared. By the way, this is also kilograms times meters all over second squared, all the same. So now we've talked about our unit for force, and we have talked about our free body diagram. Great. What else do I want to say? Let's talk about what if there are multiple forces acting and they just happen to add up to 0. 12 newtons, 7 newtons, 5 newtons. F net equals 12 minus 7 minus 5. F net equals 0. This happens a lot when there is an object that is being pushed by things, but those forces all add up to 0. That happens a lot. Like look at me right here. Do I look like I'm accelerating? I don't. So if I'm not accelerating, if A is 0, well, that must mean the net force is 0, right? Doesn't matter how big M is. If A is 0, F net is 0. This happens a lot when the net force is 0. And a lot of people say, ooh, if acceleration is 0, nobody's pushing it. Well, that's not true. Usually when an object has an acceleration of 0, it's not that there are no forces, it's that there are forces, but they add up to 0. Like right now, I'm sitting on a chair. Earth is pulling me down and the chair is pushing me up. And those two forces add up to 0. That situation is called balanced forces. The forces are balanced. The forces that push in one direction are this add up to the same number of newtons as all the forces that push in the other direction, whether that's left and right or up and down, or they all add up to 0. So when the forces add up to 0, it's just important that we don't say there's no forces, because that's not true. There are forces and they add up to 0. That's called balanced forces, and it gives us an acceleration of 0. This situation, which we figured out using Newton's second law, right? 0 net force, 0 acceleration, 0 acceleration, 0 net force. Do we need a new law to describe this? We do not. We figured it all out using Newton's second law. However, they call this Newton's first law. I don't know why. I think it's really dumb. We don't need this law. All this information is here in Newton's second law. So this very special, specific situation described by Newton's second law, they call Newton's first law. I don't know why, but there it is. That's Newton's first law. Which is why I wanted to call this Newton's law, right? Not Newton's second law. Remember, I wanted to call it Newton's law. All right. Sometimes it's called the law of inertia, but it basically says that the acceleration is 0 if there's no net force, no overall force. All right, the final thing you need to know about forces, and this will answer all of your questions throughout the whole year regarding forces. Wow, that's important. Is called the force sentence. And you can mention this to all of your aunties and your uncles and your foster parents and your grandparents and your neighbors who work at Caltech, and they'll all say, I've never heard of the force sentence, and that's okay. They didn't do anything wrong. They didn't miss a class in college. I made up the force sentence. So the force sentence is this sentence. It's very exciting. A pushes B that way. That is the sentence. Done. You understand everything. A pushes B that way. We name who is doing the pushing, and we name who is getting pushed. I don't say, B was pushed. No, I don't use the passive voice. The first word in the sentence is the pusher. The second word in the sentence is pushes. The third word in the sentence is the thing getting pushed. Now, what is most important here, or what is more important, A or B? B is more important. This sentence is about B getting pushed. So my free body diagram here, is this A? No, there's three different A's here, A1, A2, and A3 doing the pushing. We don't even draw them. This is B getting pushed. So I label this B. This is about the pushed, not the pusher. And then I draw this arrow this way just to be fun. This arrow looks more like a pull to me than a push, right? If I drew a right arrow here, that would look like a push. There's no difference between pushes and pulls. Nobody cares. So we don't make that distinction. So A pushes B that way, and we always have a direction. So always name the pusher, always name the push ed. Don't talk about, oh, B's force. B's force. There's no possession. There's no apostrophe S in forces. I don't know if B's force Is B pushing someone else or someone else pushing B? I don't know. I honestly don't know, and I'm not even going to think about it because that's not how we say the force sentence. We say who's doing the pushing and we say who gets pushed. I don't know if this force belongs to A or B. There is no belonging. There's no ownership. All righty. So we've talked about the unit for force. We talked about the force sentence. We talked about Newton's first and second law, which I just want to call Newton's laws. I'm going to tell you one more thing, and then we're going to be done. So this is the final thing. Get ready for it to be over. Very exciting. It's almost over. Earth pulls stuff down. Is that a force sentence? Yes, Earth is the pusher. Some stuff gets pushed down that way, is the direction. So if this is an object, Earth pulls it down. There's my free body diagram. Earth pulls stuff down. Done. Don't ever use the word gravity. You don't need it. Just got the pusher and the push head. Now, does Earth pull that thing? Yes. What direction? Down. How hard? So here's the answer to the question, how hard does Earth pull stuff down? I'm always going to label the downward arrow mg. Always. How hard does Earth pull stuff down? Mg. M is the mass of this object. Does Earth pull down my calculator or that piano harder? You know, you all know Earth pulls the piano down harder, right? Because the piano is made of more mass. So M is the mass of the object. G is the number 9.8. No, G is not the number negative 9.8. If this were negative, then negative down would be up. Earth doesn't pull stuff up. So G is the number positive 9.8. M is the mass. So whatever the mass is in kilograms times the number G, that is the number of newtons of force that Earth exerts on the object. Kilograms times meters per second squared, or newtons. So if this is a 3.5 kilogram object, then mg is 3.5 times 9.8. What is 3.5 times 9.8?
It's 34.3.
34.3. 34.3 newtons, because it's a force. So if this is a 3.5 kilogram object, Earth pulls it down with a force of 34.3 newtons. It just so happens that if I have a 1 kilogram object, we have measured how hard Earth pulls down that 1 kilogram object. How hard does Earth pull down a 1 kilogram object? 9.8 newtons. So 9.8 newtons for each 1 kilogram. So the 9.8 and the 9.8 and the 9.8 and then another 4.9 for the half. What is 9.8 plus 9.8 plus 9.8 plus 4.9? It's 34.3. All right, so that is Unit 2, Lesson 1 here in AP Physics 1. I'm done. I'm looking forward to seeing you again very soon. Have a marvelous day.